1. Calculate the energy required to excite the hydrogen electron from level 1 to level 3, and also calculate the wavelength of light that must be absorbed to effect this excitation. Okay, well, let's go ahead and start. So the energy 1 is equal to minus 2.178 times 10 to the negative 18 times 1 squared over 1 squared equals minus 2.178 times 10 to the negative 18 joules. Okay, so energy level 3 equals 2.178 times 10 to the negative 18 times 1 squared over 3 squared equals minus 2.42 times 10 to the negative 19 joules. Yeah. Okay, delta E, the change in energy, equals E3 minus E1, the difference in the energy levels to go from E1 to E3. You notice at E1, the energy at the one level is not 0, okay? It's minus 2.718 times 10 to the negative 18. So it still has some energy. It's not a 0 value at the ground state. There is still some energy there, okay? So the difference is 2.42 times 10 to the negative 18 joules. Now we want the change in energy. Well, we also know that the change in energy is equal to Planck's constant times the frequency of the light, which is equal to Planck's constant times the speed of light over lambda. And I'm sorry, we said we're looking for the wavelength. So wavelength is equal to hc over delta E. Delta E is that thing. So we get 6.626 times 10 to the negative 34 joule seconds times 3 times 10 to the 8th meters per second divided by 2.42 times 10 to the negative 18 joules. Joules goes with joules, second goes with second. We're left with wavelength, we're left with meter, so it confirms it, and our wavelength is going to be 8.2 times 10 to the negative 8. This is in the ultraviolet range. This means that if I want to excite a hydrogen electron, the electron in a hydrogen atom, from level 1 ground state to a level 3, that means I have to hit it with some ultraviolet light. Now, not just any ultraviolet light. Ultraviolet has a range. Specifically, I have to hit it with 8.2 times 10 to the negative 8, light that has a wavelength of that. Or I can go ahead and put it back into the equation to find the frequency, right? Frequency equals speed of light over wavelength, right? Okay, so that's it. Just some basic equations to play with. The real idea that we want you to take away from this is that electrons are traveling around this nucleus. They have different energies. You can think of them as orbits that go further and further away. As you go further and further away, those electrons have greater energy. And you can actually, electrons can jump from one energy level to another if they absorb energy of a specific frequency, because energy is quantized. They can't just make any leap. It has to be specific frequencies of energy that allow it, specific energies of light that promote it. And when it promotes it out, it drops back to a lower energy level. It emits that as light. Now, you can actually test this if you want tonight. when you're in your room getting ready to go to sleep, why don't you go ahead and just climb into bed, turn off all the lights, and if it happens to be a reasonably dark, reasonably dry day, this works better in the west than it does in the east, where it tends to be a little bit more humid, and just rip the covers off you. When you rip the covers off you, the static electricity, what you'll get this little light show. What's happening is that as you pull things away, you're ripping electrons off, you're actually exciting electrons, they're jumping up, and when they drop back down, they're going to give off their excess energy as light. Okay, so now